Welcome to this lecture number 34 on this NPTEL course on fluid mechanics for undergraduate chemical engineering students. In the last lecture, we completed the topic discussion on the topic of potential flows, wherein we showed that by constructing a solution for potential flow past a cylinder, okay, we showed that the net force exerted on the cylinder by the fluid is 0. Okay. And this is at odds with experimental observations, because experimentally, no matter how high the Reynolds number is, there is always a finite force on a cylinder, but the potential flow approximation tells us that the force is identically 0. That was called the D'Alembert's paradox. The resolution to this paradox is that one, and which I pointed out in the last lecture itself, is that since we have neglected viscous effects completely in the inviscid picture, okay, somehow viscous effects have to come back in at even at high Reynolds numbers. And the way it comes in is through the implementation of no slip condition, because if you remember, when we went from the Navier-Stokes equation to the Euler equation, we told that it is impossible to satisfy both the boundary conditions, both the normal velocity condition as well as the tangential velocity condition at a given solid surface. So, we sort of went ahead without satisfying the no slip condition, but the no slip condition is valid regardless of what the Reynolds number is. So, it is valid even at very high Reynolds numbers. So, at very high Reynolds numbers, one has to satisfy the no slip condition, but that is not possible within the potential flow theory. Therefore, there must be a region very close to the solid surface where the velocity gradients must be very, very high, because the velocity will vary from whatever it was at its free stream value, that is far away from the solid surface, and it will come rapidly to 0. And that region is called the boundary layer, and once the boundary layer is taken into account, then it is possible to predict non-zero finite forces on solid surfaces, and that is the topic of discussion for today, that is boundary layer theory. Okay. Now, one another indicator that the inviscid flow theory is extremely flawed is the following. Suppose you look at the pressure variation. Okay. I am plotting here P minus P 0 on the surface of the sphere by half rho v square. P 0 is the pressure far away from the sphere. So, this is the difference between the pressure on the surface of the sphere minus the pressure far away divided by half rho v squared, where v is the free stream velocity. So, the coordinate system is like this. Okay. You have the cylinder, okay, and imagine that the flow is far away in this x direction, okay, and we are trying to measure theta like this. Okay. So, this is theta is 0, this is theta is pi by 2, and if you come around a full half circle, theta is pi. I am plotting here pressure as a function of theta. Okay. I will plot two curves, what is observed in what is done in the what is predicted by the potential flow theory. So, theta is 0, theta is pi by 2, theta is pi. Okay. And what is predicted by the potential flow theory is something like this. Okay. So, let me draw. Okay. So, the potential flow theory predicts that the pressure is a maximum here and here, okay, at theta equal to 0 and theta equals pi. So, and it is symmetric. So, the values are the same, and it is a minimum at theta equals pi by 2. Okay. So, the pressure curve will be completely symmetric about the theta equals pi by 2 line, okay, and of course, there will be similar pressure from the, it will also be symmetric about this axis also, because that is a symmetry due to geometry, but this symmetry is because of the fact that the potential flow equations dictate that symmetry. Okay. Now, this is the potential flow prediction. What happens in reality if somebody measures the pressure as a function of the theta direction like this? Okay. So, I am going to show that in this green curve. So, it turns out that the green curve follows the prediction somewhat up to a point here. So, up to here the green curve and the orange curve, they agree with each other, but after that, okay, these are the green curve is the experimental data. After that, the green curve does not agree with the potential flow prediction. Okay. Now, because of the symmetry of this potential flow pressure distribution, we found that the force exerted by the fluid on the sphere is 0, but in reality if the pressure distribution is as indicated by the green curve, you can already imagine that if you integrate this pressure over the surface of the sphere, we may not get a 0 answer, okay, because the pressure on this side of the sphere, this is let's draw this again. What experiments are telling is that pressure on this side of the sphere is the pressure distribution on this side of the sphere is very different from the pressure distribution on this side of the sphere. So, if you integrate the pressure distribution, okay, then you can guess, or you can predict that you can foresee that it is actually going to be non-zero. So, that will give rise to a non-zero force, okay, if you use the pressure distribution that is actually found in experiments. But the potential flow says that the pressure distribution is completely symmetric about the theta equals pi by 2 line. So, therefore, you got a 0 answer. So, this force due to pressure asymmetry on the fore and aft of the sphere okay, is called form drag. Okay, this is only purely due to the asymmetry in pressure. Now, the reason why that happens is that the reason why the pressure deviates from the potential, the pressure actually the actual pressure, the green line actually agrees quite well with the orange line up to a point here, okay, but after that it starts deviating. The reason for this phenomenon is what is called flow separation. We will discuss this little in detail a little later. So, and this is what causes the pressure, the flow that was following the surface of the cylinder, it essentially deviates, it takes off from the surface of the cylinder, and that is the reason why the flow separates in a potential flow, okay, and that causes the pressure so to vary significantly, okay. And the reason why flow separates itself is because of viscous effects. So, I will come to that as we go along. Okay. Now, there are objects where you can prevent flow separation. So, how to prevent flow separation? Well, these objects are called streamlined objects. So, an example of that is the cross section of an airplane wing, which is called an airfoil. This is essentially the cross section of an airplane wing. So, if you look at a flow past such an object, okay. So, let me draw it more straight. Okay. If you draw the flow past such an object, then the flow will tend to follow the contours of the body more faithfully than in the case of flow past a cylinder, and that is because of the fact that the geometry of the body is such that the geometry of body is such that flow separation does not occur. Flow separation is prevented in streamlined bodies. So, in streamlined bodies the form drag is minimal compared to objects like spheres or cylinders where there is a significant form drag. The form drag is itself due to the pressure asymmetry between the fore and aft of a symmetric body like a cylinder, and why that pressure asymmetry occurs in experiments is because of flow separation, which we will come to shortly. Now, we will get back to what is the reason for boundary layers. Why do you need boundary layers and where do they occur? Okay. Now, as I have told you, suppose you look at an airfoil, flow past an airfoil, which is a streamlined object where we need not worry about flow separation. Suppose I look at a tiny zone and blow it up, essentially you will have something like this. Okay. You will have a slightly curved object and fluid is flowing. Okay. Now, you would expect the fluid flow to be uniform, okay. That is, the fluid is flowing with some velocity, but at the surface of the airfoil the fluid has to obey no slip condition. So, it has to come to 0 velocity boundary condition. So, there is a zone demarcated by this orange line where viscous effects are becoming important, because of the fact that the velocity, fluid velocity, which was uniform, okay, far away from the surface of the airfoil or this surface, okay, has to obey the no slip condition. So, there must be a region of fastly varying velocity, rapidly varying velocity. Now, that is called the boundary layer. Now, what has rapidly varying velocity got to do with viscous stresses? The answer is simple, because if you remember, the viscous stress is mu times dVx by dy in a simple setting. Suppose this is the flow direction, this is the y direction. If there is a velocity gradient in the x velocity in the y direction, okay, that is this quantity. If this, see what we said in inviscid flows is that the viscosity was small. Okay. When the viscosity is small, we said that we can neglect shear stresses, but that was based on the assumption that this quantity, the velocity gradients are not large. But we just showed that there are physical reasons to believe that close to a solid surface the velocity gradients can be large, because the velocity has to go very quickly from its free stream value back to 0 at the surface. So, when this becomes large, when in some sense the viscosity is small, although we have to non dimensionalize to make this argument more concrete, which I will do in a minute, but this is more like a very quick justification as to why viscous shear stresses become important in the bound layer, because you are multiplying a large quantity by a small quantity and you are not multiplying a small quantity by another moderate quantity, so that you can neglect shear stresses. So, the shear stresses become finite in the boundary layer. So, that is the key reason why shear stresses become important, and that is the origin of the boundary layer is the necessity to satisfy the no slip condition regardless of how high the Reynolds number is. Okay. Now, what has the boundary layer got to do with separation? The answer comes in the following way. Suppose you consider flow past a cylinder. Okay. As per inviscid flow theory, okay, if you draw the pressure profile, okay, if you draw the velocity profile, so this is the line of symmetry. If you draw the velocity profile, it is going to be like this. It is going to be completely symmetric about the, this is theta is 0, this point, this theta is pi by 2. So, the velocity profile and pressure profile are exactly symmetric about theta equals pi by 2 line. This is called fore aft symmetry. Now, if I look at the flow as it comes in this direction, this point A, the flow velocity comes to 0, because it is completely normal. At the surface of the cylinder there is no velocity. So, as per Bernoulli equation, the pressure here is a stagnation pressure. It's the, so this is P naught plus half V squared, but V squared is 0. Okay. Now, if you go from here, okay, from here to, so this pressure, okay, which we already know from the previous classes example, the previous class we actually discussed what is the potential flow past a sphere. We found what is the pressure distribution, and the pressure distribution which I will write down again. So, P at the surface minus P naught is rho u squared by 2 times 1 minus 4 sin squared theta. Okay. So, this is the pressure at the surface of the sphere, and if u is 0, okay, at this point there is okay, at this point, sorry, we have to just set theta at A, theta equals pi, and sin pi is nothing but 0. Okay. So, at A you get the pressure minus P naught is maximum, it is rho u squared by 2. All the kinetic energy head that was here. So, far away, if you use the Bernoulli equation, far away the pressure is P naught plus half P naught by rho plus half u squared, and that must be equal to the pressure at the stagnation point, which is P at the point A by rho plus 0, because there is no velocity. So, clearly P at the point A minus P naught is half rho u squared. This is purely from Bernoulli equation, and that exactly agrees with the potential flow solution, right. So, the pressure is maximum here. Now, as the fluid flows, if you just trace the fluid along the surface of the cylinder, here the velocity, see here the velocity is 0, the pressure is maximum from Bernoulli principle. Now, as the fluid flows along this line, here the velocity becomes maximum and the pressure at point B, okay, the pressure at point B becomes minimum. This is point B, the pressure becomes the minimum. Okay. Now, and then if you follow from point B to point C, okay, here the velocity is maximum, pressure is minimum, again it has to come to velocity minimum and pressure maximum. So, here this region from B to C is an adverse pressure gradient, is a region of adverse pressure gradient, because the fluid is moving from a region of low pressure to high pressure. Now, in the potential flow that is possible because the fluid is losing its kinetic energy. So, there is an interconversion, perfect interconversion between the kinetic energy and pressure head as the fluid moves along this point. But what the potential flow theory neglects is the viscous effects. So, as if you include viscous effects close to the surface within the bound layer, then the fluid, the viscous effects will tend to retard the fluid because of viscous friction. So, at some point, because the fluid is trying to push by virtue of its kinetic energy, and the kinetic energy is reducing because it is being converted to pressure head as the fluid particle is traveling, at some point along the surface, because of viscous effects, the kinetic energy or the velocity will come to a still, that is, it will become 0. At this point, the fluid will no longer continue to follow the cylinder, because the fluid that is flowing adjacent will tend to pull off the fluid particles away from the surface of the cylinder. So, this is called flow separation, and the region where the flow has separated, you will find what are called wakes. Okay. And this is the reason why we have flow separation in flow past objects like spheres or cylinders, because of the pressure distribution that is present in the inviscid potential flow that gives rise to adverse pressure gradient in the aft side. Suppose you look at this side, it is a region of so let us draw this line, this is a region of adverse pressure gradient. Okay, while this is a region of favorable pressure gradient. And as the fluid particle moves from here, as it moves here, okay, viscous effects become important close to the solid surface for reasons I just explained, okay, because the velocity gradients are larger. So, it tends to retard the fluid particle. At some point, the fluid particle will come to a halt, and then the fluid that is flowing away and adjacent to it will tend to pull it apart. Okay. It is not able to follow the contour of the geometry. So, this is called flow separation. Okay. But such a phenomenon is not possible in streamlined bodies, because this adverse pressure gradient region does not develop in streamlined bodies. So, this idea of reducing the flow separation is called streamlining in fluid mechanics. Okay. So, now let us go to the estimation of boundary layer size or thickness of the boundary layer by non-dimensionalizing the Navier-Stokes equation. Estimate the boundary layer thickness. Okay. So, imagine we have, so for the present, to discuss boundary layers, we will not worry about bodies such as cylinders or spheres, because we know that flow separation happens. When flow separation happens, okay, as I just indicated in the last, okay, the flow separates from the body, and there is a huge region where viscous effects become important, that is called the wake. So, our original proposition that viscous effects are not important in the bulk of the flow at higher Reynolds numbers becomes invalid. So, we have to actually now therefore, not consider this kind of problems wherein the flow separates, but if you consider a streamlined body like an airfoil, okay, flow past an airfoil, then flow separation is prevented, and then we can just imagine that the effect of viscosity will be, viscous effects will become confined only close to the surface of the solid, and therefore, you can actually use the boundary layer theory to predict forces. Okay. So, in order to do that, in order to estimate the thickness of the boundary layer, I am going to blow up this part. Okay. Locally, this is going to appear like a flat surface, because the thickness of the boundary layer is very small compared to the radius of curvature of the solid. Okay. So, you have an xy plane, okay, and there is flow, uniform flow, and close to the solid surface, this is the boundary layer where viscous effects become important. Okay. Now, how are we going to estimate the thickness? What is the thickness? Okay. Now, if you remember, when we non-dimensionalized the Navier-Stokes equation, previously we used, let us imagine that the length of the airfoil or some typical thickness of the airfoil is L. We had used the fast stream velocity u as the velocity scale and this L as the length scale in non-dimensionalizing the Navier-Stokes equation. Okay. But the variations in the direction perpendicular to the boundary layer, the length L is immaterial, it is not important. It is not the characteristic length scale for variation of velocity in the direction normal to the surface of the solid. Therefore, we have to rescale the problem. Okay, because the natural length scale for variation of velocity in the boundary layer is not the thickness of the airfoil or the length of the airfoil, it is a new length scale that will emerge from our problem. Okay. So, what we will do is we will say, so we will rescale the Navier-Stokes equation, the x direction, the flow direction we will use the length scale L, in the y direction we will use a new length scale delta, where delta is the thickness of the boundary layer, which will be determined shortly. Okay. This is the boundary layer thickness. How are we going to estimate this? We are going to substitute this back in the Navier-Stokes equation and again do the non-dimensionalization. Okay. When we do that, we will find, so the dimensional Navier-Stokes equation for this simple 2-dimensional problem, steady problem, becomes the x momentum equation, okay, is equal to minus partial p partial x plus mu partial y square, okay, plus mu partial squared v x by partial x squared. Now, upon using x star is x by L, y tilde is y by delta, okay, and all the velocities v x star is v x by u, v y star is v y by u, and so on. If you do that, okay, so what you will get? Okay, so first we will have to worry about what is v y star, how to non-dimensionalize the normal velocity. So, let us first write down the continuity equation in Cartesian coordinates. Okay. In the x, we have chosen the velocity scale to be u and the length scale to be L, plus in the y direction we do not know what the velocity scale is, let us call it some v, and the length scale is delta. So, unless v is u times delta by L, okay, this equation will not be satisfied. So, this implies the continuity equation implies that the scale for velocity is this. So, you can imagine that the velocity in the x direction is u times delta by L. Since the bound layer is very thin, we will show that delta by L is small compared to 1. We can say that the normal velocity is very small compared to the tangential velocity. Okay, so, when we use this all this information back in the x momentum equation, you will find that V x star partial V x star by partial x star plus V y star partial V x star partial y tilde is equal to minus partial P star by partial x star plus 1 over R e partial squared V x star by partial x star squared plus 1 over R e L squared by delta squared partial squared V x star by partial y star squared. Okay. Because we are using a different length scale for non-dimensionalizing the y coordinate, we are getting this new term. Now, we are going to consider the limit Reynolds number large compared to 1, because we are in the business of dealing with high Reynolds number flows. So, this term is indeed small, okay. But when you look at this term, you get a combination. This is the gradient of velocity in the y direction, okay. You get 1 over R e times L squared by delta squared, okay. Now, in order to satisfy the no slip condition, we need to incorporate this term, otherwise if this term becomes small, we will not be able to satisfy the no slip condition. Therefore, we demand that this should be similar to 1, otherwise this term will become smaller. So, this gives rise to the result that delta by L whole squared should be proportional to 1 over R e, or delta by L should be proportional to R e to the power minus half. So, this is an estimate of bound layer thickness, and as I had claimed before, it since Reynolds number is large, 1 over Reynolds number is small and 1 over root of Reynolds number is small. So, this is indeed small compared to 1. So, the bound layer is indeed a very thin region compared to any other relevant dimensions of the physical problem, such as the length of the airfoil or the thickness of the airfoil or things like that. So, it is indeed very small compared to the other physical geometrical lengths of the problem, and it is therefore, the bound layer can be said to be confined very close to the solid surface, where the velocity varies very rapidly to satisfy the no slip condition. Okay. Now, the next step for us is to see how to predict shear stresses. Once we have realized that the bound layer is important, then we have to go ahead and see what is the how to predict viscous shear stresses, and thereby how to predict drag forces on solid surfaces. In order to do that, I am going to use a momentum integral formulation. This is an approximate method that gives you a reasonably accurate answer. In more advanced classes, you will learn how to solve the bound layer theory, the bound layer governing, how to solve the Navier-Stokes equations within the bound layer approximation using suitable techniques, mathematical techniques, and that gives you a more rigorous solution to the problem, but that is beyond the scope of the present introductory course. So, we will remain content by using a rather approximate method, but which is deeply rooted in the physics of the problem, and that gives reasonably accurate results also. Okay. What we are going to do is to consider a flat plate, because remember the bound layer is very thin. So, even if you have a curved geometry locally, that is going to appear like a flat plate on the scale of the bound layer thickness. Now, I am going to consider a control volume, a differential control volume, and do a momentum balance about it. Okay. The control volume is like this, okay, of distance dx, length dx, okay. Now, let us call this face A, B and C and D, and the bound layer thickness in general is a function of the distance along the flow direction. So, flow is like this. So, flow is like this, happening like this, and this is my control volume A, B, C, D. Okay. Now, we are given how the flow varies outside the bound layer. These are the potential flow solutions. remember outside the boundary layer the potential flow solutions are valid. So, we are given that information and we want to find what is delta of x, okay. And I will claim that after you find what is delta of x, we can find the forces, the viscous stresses and so on. First let us do a mass balance. We will do a mass balance across this control volume ABCD. Okay. Important to note here that this is not a streamline, the BC is not a streamline, it is merely an imaginary boundary that separates the boundary layer from the outside inviscid free stream flow. Okay. So, that is it is not a streamline. So, all I am trying to imply is that fluid can enter through the surface BC. So, when you do the mass conservation integral mass balance for this CV, then you have to actually take that into account. So, at steady state the mass balance implies A is 0 over all the control surfaces. This implies that m dot AB plus m dot BC minus m dot CD is 0. There is no flow across AD because this is the velocity satisfies no normal velocity condition at the surface, rigid surface AD. So, this will essentially boil down to this. So, this implies that m dot BC is nothing but m dot minus of m dot AB minus m dot of CD, where m dot at AB is the mass that enters through this, okay, and m dot of CD is the mass that leaves through this. Okay. We have to work out the signs appropriately as we go along. So, m dot AB is nothing but, since the unit outward normal is to AB is in the minus I direction, because flow is in the plus I direction. So, there has to be a negative sign in calculating the mass flow rate. It is nothing but integral 0 to delta rho u dy times w. This is the width into the plane. Since we are considering that to be a very large quantity, so we can just multiply all our results by the width to get the appropriate dimensions, width into the plane of paper or the plane of the board in which I am writing. Okay. Now, m dot of CD is nothing but, okay. So, here for CD the direction of flow and the direction of unit normal are both positive. So, I can write this as W integral 0 to delta rho u dy evaluated at x plus delta x, because this is no longer, okay, at the value at x. So, I can write this as m dot at x plus d m dot by dx evaluated at x times dx. Okay. So, m dot C D is nothing but W integral 0 to delta rho u dy plus W d dx of integral 0 to delta rho u dy times dx. Because delta is a function of x, okay, we have to take this. Okay. This is an integral, but the integral is a function of x through the fact that delta is a function of x. The upper limit is actually a function of x. So, you get therefore, m dot B C, the amount of mass that enters through the top surface B C of the control volume, that is this surface where I am showing the yellow lines here. M dot B C is nothing but minus W partial x of integral 0 to delta of x rho u dy multiplied by dx. Okay. This is m dot B C. Okay. All this is saying is that if delta is a function, okay, of, if delta is actually a function of x. So, this is delta, it is a function of x, then m dot B C is actually a negative quantity, that is fluid has to leave through the surface B C. That is precisely because of the fact that, okay, the areas are changing through which the fluid is flowing, they are changing. Okay. So, and that is the reason why, and this is coming out to be negative. Okay. So, momentum balance the momentum balance says that for the CV ABCD says that the sum of all the forces. So, let us write the x momentum balance, sum of all the surface forces exerted. I mean, we will neglect body force in our current discussion. Sum of all the surface forces is equal to the momentum flux at steady state u rho v dot dA. Okay. So, we will come to what the forces are a little later. So, we will first focus on this term. This is equal to the momentum flux through AB plus momentum flux through CD plus the momentum flux due to BC. Okay. There are these three phases through which momentum can come in by virtue of flow, AD, CD and BC. Okay. These are the three phases, and the bottom phase is impermeable. So, there is no momentum flux. Okay. So, if we now calculate what are the momentum fluxes due to all these three phases, this is nothing but minus of W times integral 0 to delta u squared rho dy. CD is nothing but W times integral 0 to delta rho u squared dy plus W d dx of integral 0 to delta rho u squared dy, and here this is nothing but u times m dot bc, because the fluid is coming with a constant velocity at the top surface. Okay. And since the surface is curved, the fluid is entering and it will bring in some momentum. So, that momentum is the mass flow rate times the velocity of the fluid, which is u times m dot bc. But we had just calculated what is m dot bc just now in the previous mass conservation. So, we have calculated what is m dot bc, it is here. So, we have to simply use that. So, this is nothing but minus u partial by partial x of integral 0 to delta rho u dy dx times W. Okay. Now, what are the forces? Because you have to now worry about the forces on various phases. There are pressure forces and there are shear stresses exerted by the solid surface. Okay. Forces on the CV. So, we have to now worry about what are the forces on the CV. Let us draw the CV again. So, this is the edge of the bound layer, and so we are considering something like this, A, B, C, D. So, I will draw A, B, C, D again for you, A, B, C, D. So, here there are pressure forces at the face A, B, there are pressure forces on this curved surface B, C, there are pressure forces on this straight surface C, D, and there are viscous shear forces which will tend to drag the fluid in the minus. Suppose this is the flow direction, which is x, the normal direction is y. So, there will be shear stresses here. So, these are the four forces that will act on the fluid in the CV. So, let us write down all the forces. On the surface AB, you have force is pressure times the width into the board times the area so let us just, so this is delta at x. So, the force is the pressure times the cross section area, the cross section area is W times delta x. The force on the face CD, and this pressure is acting in the plus x direction, while the force on the pressure force on the face CD will be acting in the minus x direction. So, the force is minus, after doing a Taylor expansion, P plus partial P by partial. So, let me write all the steps for convenience, for clarity, is P W times delta at x plus delta x, at x plus dx. Okay. This is nothing but, and minus, because force is in the minus x direction, this is nothing but minus p plus dp dx at x, okay, sorry, okay, dx times minus p at x times w times delta plus d delta, because the boundary layer thickness also will change from delta to delta plus d delta by dx times dx, which is nothing but d delta. Okay. So, that is what I am writing here. This is the force on the face CD. Now, we have to worry about force on the face BC, the curved surface of the top of the edge of the bond layer, okay, and that is only pressure force. What we will do is to take the average of the pressure here and pressure here, okay, and divide. Let us assume that to be the pressure, and we have to multiply it by the projected area, because it is a curved surface area. So, we have to multiply it by the area projected on the x direction, okay, that will be the force. So, if you do that, and it will be in the plus direction, because the force is acting along, the pressure is acting along the x direction. So, the average pressure is half p at x plus p at x plus dp dx times dx. Now, we have to multiply it by the projected area, which is d delta times w, because this change in the bond layer thickness is actually d delta, and that multiplied by the width into the paper will give us the force acting on the surface BC. Now, force on AD, the bottom surface, the viscous shear stress is, and the viscous shear stress will tend to act in the minus x direction, because it will tend to retard the fluid. So, F AD is tau w at x plus tau w at x plus dx multiplied by w dx. Okay. So, this force is acting on a strip, which is dx, and w into the board. So, but we are taking the average shear stress between the point at x and point at x plus delta x, taking the average. So, that will eventually, after Taylor expansion, this will eventually become tau w at x plus half d tau w, okay, times, and it is in the minus direction. So, as I have told you, so times w dx. Now, I have to put all these things together. Okay. The net force is the total force in the x direction, net in the x direction will be, therefore, the force on the face AB, which is P w delta, minus the force on the face CD, which is minus P, okay, plus dP dx dx times w times delta plus d delta. Okay. Now, plus the force on the face BC, which we can simplify it as P at x, okay, times plus rather half dP dx dx times w times d delta, okay, that is the projected area, minus the shear stress, which is tau w plus half d tau w times w dx. This is the total net force. Now, that after, okay, let us cancel out stuff. So, let us first we have to expand this, but we can cancel out just by ready inspection also. This P w delta will cancel this P w delta. Okay. So, P w delta is gone, but there is also another term. Okay. So, we will write down terms that are non-zero. So, we will get minus P w d delta, that will cancel plus P w d delta. Okay. So, P w delta cancels with this, then P w d delta will cancel, okay, with this term, okay, and then you will have terms of the type minus dP dx dx times w times delta. So, we will write this down again, minus dP dx dx w times delta minus dP dx dx w times d delta, okay. And then you have plus half dP dx dx w times d delta, okay. And finally, you also have the shear stress terms minus tau w w dx minus half d tau w w dx, okay. Now, we are going to throw away terms that are squares of differentials. So, this is there is a differential of stress and differential of length, this is small. So, this is again small because it is dx d delta small, again dx d delta small. So, the only two terms that will survive from the net force is this, okay. So, you will finally get the net force in the x direction is nothing but minus dP dx delta dx minus tau w dx whole multiplied by w. Now, this will be equal to the momentum flux. If you remember, the momentum balance says that the net force is at steady state, the net force is equal to the net momentum flux out of the CV. So, that we can simplify it to be d dx of integral 0 to delta of x u squared rho dy, okay, times dx minus u d dx of 0 to delta rho u dy times dx, and this entire thing is also going to be multiplied by w. Sure enough, w's should cancel from both sides as they do here, otherwise we have made some error in the calculation. But so clearly w's which are the width into the plane of the paper, they must actually cancel out, which they do, okay. Therefore, if you do everything, finally what we get is the following, okay, minus delta dP dx minus tau w after dividing by w dx in the entire expression is d dx of integral 0 to delta of x rho u squared dy, well I am for a okay, let us just write that minus u integral d dx of integral rho u dy. Capital U is the free stream velocity outside the boundary layer velocity, okay, and that is outside the boundary layer. Now, dP dx is the pressure gradient within the bound layer, but suppose this is the our CV, okay, this is the edge of the bound layer and our CV was something like this, and dP dx is the pressure variation within the bound layer. But since the bound layer is very thin, usually what happens is the pressure gradient that is outside gets impressed upon the pressure gradient within the bound layer. That is because pressure variation in the y direction, if this is the x direction, this is the y direction, the pressure variation within the y direction in the bound layer is negligible. That is, dP dy is 0 within the bound layer. Therefore, we can set dP dx outside as the dP dx within the bound layer, but outside dP dx is nothing but whatever is found from Bernoulli equation, okay. The Bernoulli equation says that dP dx, or the Euler equation which says that dP dx is minus rho u du dx. At steady state, the Euler equation for a one dimensional flow like this outside the bound layer, the flow is largely one dimensional in the x direction. So, we can use the Euler equation to find what is dP dx, and also note that delta is integral 0 to delta dy. So, if you just integrate dy to 0 to delta, you get delta. So, you get tau w is, we are eliminating the previous expression for tau w because that is the quantity of interest. We want to know what is the wall shear stress. on a boundary layer flow. Okay. So, minus d dx of integral 0 to delta u rho u dy, this we already had, plus u d dx 0 to delta rho small u dy, okay, plus you had the pressure. Instead of that, I am going to use that Bernoulli equation, wherein I am going to say that it is du dx, okay, times integral 0 to delta rho u dy, because we had just a delta that came in, the pressure gradient was multiplied by delta in the previous expression. If you see, there is a delta, and instead of delta I am going to write this as 0 to delta dy, and instead of pressure gradient I am going to use minus rho u du dx. Okay. This is the simplification that we are doing. Okay. So, the shear stress finally becomes, after doing some simplification, this becomes, so we can pull rho u inside the integral because rho u is independent of y. Okay. That is the reason. So, shear stress becomes du dx integral 0 to delta rho capital U dy minus d dx of integral 0 to delta u rho u dy plus u d dx of integral 0 to delta rho u dy. Okay. Now, I am going to split the last integral in the following way. Now, I am going to write this as d dx of integral 0 to delta rho u dy minus du dx of integral 0 to delta rho u dy. Okay. The last integral can be written like this by product rule, because both u and delta are functions of x. So, here u is out, so I am bringing u in, but then I have to subtract an equivalent term. This is just product rule of two multiplication of two functions. Okay. So, tau w then becomes, now if you look at this expression, this has similar form like this, but only key difference is this is capital U, this is small u. So, I can rewrite this as is du dx, I will take that as common, 0 to delta rho capital U minus small u dy, okay, that is one term. Now, the other term will remain the same, minus d dx. Okay. So, the other term, so we have this term rho u, here you have u rho times capital U. So, I can do a simple manipulation and take this common, d dx as common, you get 0 to delta u rho times capital U minus small u dy. Okay. So, this is my expression for the shear stress on the surface, which is a function of x. The shear stress is not a constant, because remember everything is a function of x, because delta is a function of x. So, shear stress will in general be a function of x. Okay. So, I am going to rewrite this slightly. So, tau w is partial by partial x of u squared of integral 0 to delta rho, okay, u divided by u times 1 minus u divided by u. All I am doing is to take this u out, and then I write d dx of du dx as d dx of u squared, okay, 1 minus u by u dy, okay, plus, okay, I am sorry, there has to be a plus sign here, because I am using capital U first. So, capital U is multiplied by a plus here. Okay. So, it's capital U has a plus term. So, this is a plus, not a minus in this expression. So, plus, therefore, u times du dx of integral 0 to delta rho times 1 minus u by u dy. I am just rewriting this expression. Now, this expression is important because the moment I tell you what is the velocity profile in the bound layer and what is the free stream velocity profile, we can actually evaluate this integral. Okay. Now, in order to do that, we have to actually solve for the bound layer velocity profile, which is difficult in general. We have to do sophisticated you have to use sophisticated mathematical techniques to solve the bound layer equations, but here we will be content with doing simple approximations for what is the bound layer velocity profile, which will then give us how the shear stress varies as a function of the distance. We will stop here and we will continue in the next lecture and complete this discussion on momentum boundary layer analysis, integral analysis of the boundary layer.